Hello and welcome to the first video in a course on machine learning. The purpose of this course is to go over the material you'd see in an undergraduate course on machine learning in the CS department or in an engineering department. So before we get started, as you may notice from my channel, I'm actually a mathematician. Um, so I plan to give I'm not planning to make this like a math course or something, but I'd rather try to give some like insights for why things work without making it too much complicated. So it's really a CS course, but probably we're gonna be giving a little details here and there when necessary. Um, and I'm hoping after this course that people will start appreciating why things work. Though we can't justify everything, but like some math can be said here and there um, um, when there's a need to. So before we start talking about today's lecture and the purpose of it, I should probably tell you what's the big overview of big idea, like the big idea of machine learning and what is it about, right? So machine learning is actually can think of it. Machine learning, it's just a subfield of another bigger field called artificial intelligence. Um, Let me just call it AI. In machine learning, what we do is that um like we try to construct statistical algorithms that can learn from data. In the sense that like you try to train some sort of algorithm to predict some pattern in a data that is fed to it. And we try, after doing that, we try to use this like predictor to predict labels on unseen data. So I said some buzzwords here, um, but probably if I tell you to look at this picture here, um, you can think of every dot here as like as a data. You can think of it as a data point. Um, so we can be talking about, for example, predicting houses prices. Like you can think of, let's say this is the housing price. You can think of us using, for example, the the size of the house in square footage, for example, to predict the price of the house. And we can like take so many samples. We can take so many samples of like sizes versus prices, and we can plot them, and we can try to predict the pattern. So, for example, if we try to predict the pattern of what's happening here by a straight line, by this red straight line, um, we don't want to draw a straight line like this because this doesn't illustrate the pattern that's happening in the data. We don't want to do something like this. We don't want to even do something like this because it's not good. So what are we really trying to do? Well, we want to fit this line that is um we want to fit a line that is best like that is best predicting the pattern appearing in the data. And um we can actually translate this mathematically and like we can translate it to a minimization problem. So by that I mean if you look at this line that I claim this is the best line predicting what's happening in the data. You see, what we're really trying to do is that we're trying to minimize. So we're looking at the distance between every point and the line, and we're trying to make this distance the smallest, right? So we're trying to put a line here, We're trying to put a line in the plane that makes this distance the smallest. So, so this can be translated to math. This can be translated to a math problem, and we can solve it. So, so for example, if we were to take this line, this won't be a good choice because I mean, the distances here would sum up. Like if we sum all these distances, we'll see that this line is bad compared to this line. So, so one can argue that this red line is actually the best line among all the possible lines that can be constructed. All right, so now that I've given you the big picture, let us now take a digression and understand how to do minimization. So let me just remind you of, so in this lecture, let me just remind you of some calculus concepts that you need for the machine learning intro course in general. And we're gonna then, in the next video, in the next lecture, we're gonna talk about specific concepts in machine learning. So today's video is gonna be about the math needed to start machine learning. So as we saw here, we like there's a need for a tool that allow us to minimize something. And we're still not clear what we're minimizing here, but it's gonna become clear in the coming videos. But I want you for now to just think that there is something that we want to minimize, and once we minimize it, we get this best predictor of the pattern that's happening. So here's the general setup. The general setup that's going to be needed for machine learning problems is that we're going to be needing like there would be some function defined on R to the D that is real valued, and we want to minimize it. We want to find the x corresponding to the minimum value of f. We already know, like we already know from um, like for example from calculus, if we had some function like this, then we'd say, bam, this is the minimum that we're looking for. But like when we go to R to the D, like when we're no longer working in the D equals one case, the problem becomes harder, and we'd need some tools to deal with this. So so basically, if you remember from calculus, for example. The way we used to find local minimum and global minimum, one way that we used to do this is by like finding the critical points of the function, and then try like the critical points are generally candidates for local min, right? And we used to use some tools like the second derivative test or the first derivative test to actually tell whether this critical point is local min, local max, or a saddle point. And this was the main tool that we used there. So what we're gonna do here, we're gonna like illustrate what assumptions do we need to put on the function so that finding the minimum is easy, right? Because when we go to R to the D, there's still an analog of this first derivative, second derivative test, and so on. But it gets a little bit harder to deal with these. Um, so what we're gonna do is we're gonna go ahead like I'm gonna go ahead and explain um, what does it take for the function um, or for a critical point to be a local minimum, and And from there, if we assume that the function that we're trying to minimize has these conditions or has these nice properties, then we can follow that procedure to get the local min or the global min in general of any function of interest that has these nice conditions. So the purpose now is to identify what nice conditions need to apply on the function that we're working with so that we can get its minimum easily, right? So let me remind you real quick of the definition of a local min and a global min. So a local min, um, it's actually a point where like the function f takes the smallest value in a neighborhood of of that minima, in the sense that like we have some function like this and so on. For example, if we have something like this, then we see that this is a minimum. This is also a minimum, and this is also a minimum. But these are not global min. So in this case, probably this is the global min. This is the one that is the smallest, right? But like this point, it's not a global min, it's a local min, right? Because if we look around that point, we see that it takes the smallest value in a neighborhood of that point, right? If we look at a neighborhood of that point, it takes the smallest value among the values taken here. So I hope that this is clear and reminds you of your calculus course. So a global min, however, as we mentioned, it's a point where f takes the smallest value for any x, not just in a neighborhood of that point of that minimum. It takes the smallest value everywhere, right? So if you were to choose any point in R to the D in the domain, the value of f would be bigger than the value of f, bigger than or equal the value of f at that global min. Okay, so for us to answer that question, we need some definitions before we get into some theorems that will help us with that thing. So let me just remind you of a few things. If we have a function that, so remember, our f here is, its domain is R to the D, and it's real valued, and we want to find what's so-called derivative of it, right? But since we're not working with a function defined in R anymore, we need to deal with the gradient instead. So the gradient of a function f on R to the D, remember f is a function whose input is a vector in R to the D. So this is how f can be defined. And what we're gonna do is we're gonna differentiate f with respect to every single component of it, and we're gonna stick these in a vector, and this is gonna be called the gradient, if you remember this. Now, also, since we're working with functions on R to the D, then we can't really remember when we were talking about the second derivative test and so on, we had to calculate the what we called f double prime, or the second derivative of f. So to do it here, we need an analog of this for functions on R to the D, and this is gonna be called the Hessian. So it's the Hessian matrix, and we're gonna denote it with this notation, nabla squared of f of x, and we're gonna define it to be the matrix where every component in that matrix is defined as follows. So maybe if I tell you the ijth component, that would be easier for you. So the ijth component of that matrix, it's gonna be So you're gonna take del f by del xi and then del xj. Okay. So for example, this entry, it's the entry, it's the 1D entry of H, the matrix H. So what we're gonna do, we're gonna differentiate F first with respect to D, with respect to XD, and then we're gonna differentiate it with respect to X1. This corresponds to I equals 1 and J equals D, and so on and so on and so on. One nice thing to remember is that in the Hessian matrix, the diagonal entries are gonna be of this form, right? So the second one is gonna have a 2 here, the third one gonna have a 3 here, and so on. So it's gonna be the second derivative of f with respect to the ith component. So this is how the diagonal entries are defined. So we're gonna assume some nice conditions on the function later on, so that the only thing we need to do, if we're dealing with nice function, like we only need to get the gradient. So we only need to remember how to get the gradient and set it equal to 0, and like it's the 0 vector, and we get the solution, we get the minimum. But for that, we need to explain why this makes sense. Why taking the gradient and setting it equal to 0 is the right thing to do, right? Because like when we were doing Calc 1, for example, um, taking the derivative and setting it equal to 0 gives a critical point. It doesn't give a minimum. So, what we're trying to do in this lecture is trying to explain why it makes sense to take to take the gradient and set it equal to 0 and get the solution. So we're trying to explain why that makes sense. Okay. So, just a bit of terminology here. If the gradient exists, we say that the function f is differentiable at x. If it exists everywhere, we'd just say it's differentiable. If the Hessian exists, we say that the function is twice differentiable, and like just the usual notation from calc. And if this is an important thing to remember, if all the second derivatives are of f are continuous, so if all the second derivatives of f exist and are continuous, then this matrix H, it has to be symmetric, right? So the entries um, above the diagonal should be the same as the entries below the diagonal. So this is something nice to that is nice to remember. Okay, so this is the terminology that we need, and now we're gonna state the tools, and then we're gonna see where this brings us. All right. So the first tool that we need to state is the what is called the first necessary condition. So this is what we know from calculus. If f is differentiable and we have a local minimum, then it's necessarily a critical point. In the sense that the derivative of it, or the gradient of f at that point, must be the 0 vector. So this is something that you expect. What are like we already know that like local minimum is a critical point. If a point is a local minimum, then it's necessarily a critical point. And this is what this theorem is saying. Um, we already know that if something is a minimum, then the gradient at that point must be 0. But we don't know the other way around. We don't know if the gradient is 0, then this point is a local min. So be careful here that the if-then statement is like, this is what we're assuming, and this is what we're getting. It's not that we're assuming this and we're getting this. So in other words, it's not true yet that if the gradient of of some function f at a point is 0, then that point is a local min. So we already know one direction. We already know one statement, but that's not enough for us to know what the local min is. So this brings us to um, let's talk about the second now, the second necessary condition. So if you remember from the second derivative test in Calc 1, so we used to say that like if we have a function that's nice, like twice differentiable, continuously differentiable, and we know that the second derivative, and we know that a point is a critical point, and the second derivative at that point is non-negative, then like the second derivative at that point is positive, excuse me, then we know that that point is a local min, right? So this is what we know from Calc 1. Over here, in the R to the D case, we have an analogous thing, we have an analogous theorem, but this is also a necessary theorem, meaning we don't know the other direction. In other words, here's what we know. If f is nice, if it is twice differentiable, meaning the Hessian exists, and the partials are continuous, then um, if x star is a local min, if it's a min, then what we know is that the Hessian matrix at that point is actually positive semi-definite. And by positive semi-definite from linear algebra, this is actually this means that every point, if I take that matrix, if I take that matrix and multiply it by a z vector, and then I multiply it by z transpose in the beginning, then that ought to be non-negative for every z. That's very important. It's not for one z, it's for every z. So positive semi-definiteness is a necessary condition if the point is a local min, but it's not sufficient. It's not sufficient in the sense that if we know that the Hessian exists and it's positive semi-definite, that's not enough for us to tell that the point is a local min. So we see that some conditions are missing. It's not enough to assume that the derivative exists. It's not enough to assume that the derivative exists and set it equal to 0 to get the local min. So there is something that we're missing that we need to assume about the function so that we can do that safely and get the local min. So what is it that we're missing? Okay, so before we do that, before I answer that question, I guess I should tell you briefly, um, as an example, for example, to keep in mind, look at this function. You don't want to do the mistake of taking the gradient and setting it equal to 0, for example, because that won't give you the right solution. It won't give you the minimum because I mean, if you look at the gradient of this function, what's the gradient? We're gonna take del f by del x1 and del f by del x2. And if you find this gradient, you will see that this is 4x1 cubed, and you have here minus 4x2 cubed. And then setting this equal to the 0 vector gives us x1 equals x2 equals 0, meaning the x star would be 0, 0, meaning our claim our claimed minimum would be 0, 0, but this claim is false because 0, 0 is not a local min. And why is it not a local min? Well, it's because if you take this to be 0, if you take x1 to be 0 and x2 to be um, any, for example, small number, you would see that this quantity would be negative. But this would mean that the value at 0, 0, the value at x star wasn't the smallest because the value at x star is 0. It's 0 to the fourth minus 0 to the fourth is 0. So the value at x star is not the smallest. So so we basically need um we need some more tools. That's not enough. It's not enough to take the critical point. And as as an illustration that this theorem is not enough to give us this conclusion, you can really think um, you can compute the Hessian, take it as an exercise and compute the Hessian and see that the Hessian matrix will be the zero matrix. And the zero matrix definitely satisfy this. Because if I multiply the zero matrix by any vector and multiply it by the transpose of that vector, I'll get the zero quantity. So the Hessian matrix in this case is in fact it is in fact positive semi-definite, but we don't have that x star is a local min. So just be careful here um when dealing with these theorems. So there is something more that is needed to be assumed. Okay, and let's see what that thing is. Okay, so it turns out, mathematically speaking, the thing that we're missing is something called convexity. So we're missing some mathematical concept that is called convexity. And once we have that the function is convex, it turned out that things are nice and it's enough to take the gradient of the function and set it equal to zero and get the solution, get the local min that you're looking for. But what the heck is convexity? So I can really define it to you in this way, and that is fine because you need at least to know it, at least culturally speaking, you need to know what convexity is. But instead of doing this, let me just give you like a picture idea of what it is. Um, so the idea of convexity is that the function takes the shape of a cup, right? If the function takes the shape of a cup, and if I take the gradient and zero it out, then I'll probably get the minimum. So if I take the gradient of the function and zero it out where the tangent is the horizontal line, then that point is probably the minimum. But but what does it mean for a function to take the shape of a cup? So if we want to do this mathematically, if we want to give this a mathematical definition, then here's how one would do it. We'd say for any 2 points x1 and x2, if you look at the value of the function here and the value at the function here, and you take a linear combination of these. If you take t between 0 and 1 and you take a combination of the value of f at x1 and the value of f at x2, it's gonna be a point here. So if we take this combination, it's gonna be this point. Convexity says that the value this quantity over here must always be bigger than the value of f at the linear combination of the x1 and the x2. So this is how you can think of it. So yeah, so this is how you can think of convexity. This is the mathematical definition of it. And but I won't bother explaining this much. You can just really take it as is. This is the definition. You need to I mean, there's like a definition cannot really be explained. It is what it is, right? Um so a function is convex if the value at the linear combination of 2 points is always less than or equal the value of the linear combination of the values at these points. So this is how we can think of it. All right, so there's one little more thing that I want to say, um, which is that if this inequality is strict, we say that the function is strictly convex. Okay. So as an example, you can plot the functions. You can go to Desmos and plot the functions uh, and you can plot the function. For example, if you plot the x squared function, this is what we have. This is the x squared function, and it does take the shape of a cup. Or you can verify it using this definition. Um, that it is actually convex. So why are we doing all of this one more time? So we're doing all of this because um, the property that we were missing is the convexity. So now if we have a function that is convex, and we're asked to find its local min, then it's enough to take the gradient of it and set it equal to zero, and the point that you get will be a local min. What's even nicer is that convex functions have the property that local mins are always global minimum. So if you have a global minimum, it's going to be always a global minimum. So this is a very nice property of functions that allow us to find local mins easily. And it turned out that these local minima that we find are gonna be global minima. I was going to explain this in details, but I just literally said that. So you can just read these key theorems that are going to be needed as we go on in the course. And the main theorem that you need to know is basically this one. If we have a if we have a function that is differentiable and convex, if I zero out the gradient, then it is a global min. A point that zero out the gradient is a global min. So I'll stop this video here, and we're going to continue in the next lecture talking about machine learning concepts. Thank you.